and get the slideshow in place. Even turn on projector today. Now, before we get going, the only announcement I know about is the Alabama A&M North scholarships that there will be offering to students who are, let's see, but Lawson State is a partner with A&M, so the link is provided there. You can find out all about it to apply for the scholarship and the internship program. Now, one of the students that in my other class, he found about the scholarship, but didn't see anything specific about an internship program. Of course, he was reading on his phone, so he may have missed it. But anyway, go check it out. You got the email just as well as I did. It has a link there. You can go and find out more about information, application, that kind of stuff, what's required. Any questions? Anything we've covered so far? Let's get started then on, we're still in Chapter 2. In fact, we're in the last section we're going to cover in Chapter 2. And Chapter 2 is differentiation, fun chapter, okay? And 2.5 is implicit differentiation. Now, any of you have a gut feeling for what's the difference in explicit and implicit? Okay. We'll distinguish between functions when in implicit form and explicit form. That's one of the first things we'll do. Then we'll use implicit differentiation to find the derivative of a function. Okay? And you'll see they are usually written in such a way you can't do it the regular way. But it's a pretty simple process to do it. So let's look at implicit and explicit functions. Most of the functions we've run into so far have been in explicit form, like this. Y is equal to 3x squared minus 5. Okay? In other words, f of x is equal to 3x squared minus 5. The function is written completely as a function of x, f of x. Okay? The variable y is explicitly written as a function of x. Some functions, however, are only implied by an equation. Okay? Okay. I was going to say this is an explicit function. What are they talking about here? This function, y is equal to 1 over x. That's an explicit function. Y is defined as a function of x. But if you rewrote this as xy is equal to 1, that's not an explicit function of x. It is a function. It is it can be graphed. Everything else can be done to it. You can take a derivative of it. But this is in implicit form, not explicit. Once you divide by x, you got it in explicit form. This one was easy. You could get it into that form. However, okay, there are cases, very much so, where you cannot ever, or it would be very, very difficult to get it in explicit form. So that's what we're going to be dealing with here. So to find dy dx for the second equation, this one, not writing, you can write y explicitly as a function of x, then differentiate. All right? How would you write that as a function? Y as a function of x? Old man slower, huh? Okay. All right. Let's get Griffin here. Okay. How would you write this implicit function as an explicit function? Y is a function of x.
Y is equal to 1 over x.
Okay, yeah, you read that from before. Okay. Yeah, you divide both sides by x. Isolate the y. Get it explicitly in terms of x. And that's what we did. Once you got it in that form, I would suggest, like they did, write it in exponent form rather than denominator form. Boy, this light is really doing some flashing on me. And then how do you take a derivative of that? What would that be? somebody. Say again? Negative 1x to the negative 2, okay? And that, if you wrote it back in fractional form, what would that be? Yeah, was that aggravating?
Negative 1 over x squared.
Perfect, negative 1 over x squared, okay? So, that's one approach to an implicit form. If you can write it explicitly, do so, okay? However, not all of them will be easy to do that way. And I thought Cedric came in. All right. Anyone else come in since I called it roll? I don't think so. Okay. This strategy works whenever you can solve for the function explicitly. You cannot, however, use that procedure when you are unable to solve for y as a function of x. If there's no way you can isolate the y as a function of x, then we've got to have another procedure. Okay? Now, here's one. Okay? For instance, how would you find dy dx for this equation? Now, I want you to notice something that they said and didn't say. They didn't say for this function. Because this is an equation. It's not written in function form. Okay? I'm not saying it's not a function. It can't be expressed as a function. Well, it can't be expressed as a function, but anyway, they left it as an equation. You want to try to solve for y? Knock yourself out. Okay? Closest you could do, you could move these over there. Actually, I think I'd move the 2 over here, move these over there, and try to solve for y. If you factor out a y, then you have a term with 2y squared plus 4. In fact, you could factor out a 2 if you wanted to as well. But how are you going to get rid of that? How are you going to separate that? If you come up with a way, let me know. I'll nominate you for the Fields Medal. Okay? They don't give a Nobel Prize in math. I think Nobel didn't really like math that much, so he didn't leave any money for that. So they gave him the Fields Medal instead. Okay? No, you can't. For this equation, it is difficult to express y as a function of x. It didn't say impossible, but very difficult. To find this y, dy dx, use implicit differentiation. Now, I have a feeling they're going to wait and tell you what that is. Since I've got it on the board here, I think this will be, no, it'll be close to it. Let's go on and do it, okay? What are we trying to do? Find dy dx, right? That's what we're looking for, okay? You can't separate the y's, get it explicitly as a function of x, or not easily anyway. So what we do is just, what's the Jesus answer in Cal 1? Take a derivative, okay? So let's take a derivative of everything on both sides. Sound like a winner? Okay? What's the derivative? Let me get my pen set up. Okay. What's the derivative of 2x? I'm sorry, of x squared. Duh. Freudian, okay? 2x, excellent. Really, that was clever to come up with that. Okay. Minus. Okay. Now, what's the derivative of 2y cubed? Now, remember, we're taking derivative with respect to x. So our assumption here is y is a function of x. Okay? So what's the derivative of 2y cubed? 6, say again? A little louder. 6y. 6. Okay, wait. I can't get this to disappear. 6y squared, then times dy dx. Okay? Or y prime. I like y prime better. It's easy to write. Do you see what we did there? It's kind of a chain rule. It is a chain rule. Okay? We first took derivative of the outer function, 6 minus 6 y squared, and then we take derivative of to the inner function, y prime. We don't know what it is, but we just write it as y prime. Make sense? Yeah or nay? All right. Next. Plus 4y prime, okay, is equal to 0. Derivative of a constant is 0. Hey, what have we wound up with? We've wound up with an equation with x's and y's, but also y prime. So let's isolate y prime. That's what we're looking for, dy dx, which is what y prime is. So let's isolate them. What would be your first step to isolate them?
Separate from the x and the y.
Exactly. Get all the terms with y prime on one side and all the terms without y prime on the other side. So let's add 6y squared y prime minus 4y prime, you see why I did that, to both sides. So that'll be 6y squared y prime minus 4y prime, okay, because these go to 0. What do we have now? Yeah. Okay, it's okay to do it. You could have subtracted 2x from both sides, but then you'd have a bunch of minus signs. I don't like minus signs. Okay. So, what we have now is 2x. These all disappeared. Is equal to 6y squared y prime minus 4y prime. But you know I don't want all that mess in with my y prime. I want to know what dy dx is. So what do we do here? All right, factor out the y prime from this side. So this will be y prime times what? 6y squared minus 4. Now what do we do? And that's equal to 2x still. Do what?
Divide the y prime.
Oh, it's going so well up to that point. We want y prime by itself, right?
So
Yeah, divide the other thing out. 6y squared minus 4 on both sides. And this disappears. And now you have dy dx, which is exactly what we're looking for, is equal to 2x over 6y squared minus 4. Now, guess what? It's not an explicit derivative of x. It has x in it. It has y's in it. That's okay. We're looking for dy dx. And there we found it. Nothing said we can't have y's in there. If we could have solved for y, we could plug in what that y is and make it in terms of x, but we don't know what that is. So, any questions? We probably weren't supposed to do that at this stage, but I thought they gave us a perfectly good problem. Why waste a good problem and do it? Okay? Any questions? All right. Now, we'll do example 1, which is a step backwards. Pretty easy. Question? Or did I get something wrong?
No, I don't think you got anything wrong. I was just wondering why you didn't take out 2 to simplify.
Oh, you certainly can. I hadn't noticed they were in there. You certainly could do that. That would be 2 times x over 3y squared minus 4. That makes you feel a lot better, doesn't it? Yeah, okay. All right. It's fine. Either one of those are good. I didn't even notice everything was divisible by 2. What's that? Wait a minute. It's 2 over 2, right? So, yeah, that's a much simpler answer. Okay, sorry about that. Oh, picky, picky, picky. What's 4 among friends, huh? Good observation. Okay. Maybe now I've got it right. That's no wonder they didn't do the one in the book. Okay, all right. Good observation. Yeah. Simplify as much as possible. The reason I didn't do it, I want to take off a point for you. No, I'm sorry. Any questions on that? Any other questions? So let's move on. Okay. All right. 2. Wow. Yeah. More verbiage before we get to the first example. To understand how to find dividing x explicitly, you must realize that the differentiation is taking place with respect to x, not with respect, with respect to x. This means that when you differentiate terms involving x alone, differentiate is normal, okay? However, when you differentiate terms that involve y, you must apply the chain rule, yes, our favorite, because you're assuming y is defined implicitly as a differentiable function of x. If it isn't, then the whole problem doesn't make any sense. If it's not a differentiable function, you can't take the derivative, okay? So that's our assumption here. And when I was in the Navy, they had a phrase for what assume means, but we won't go into that either. Okay. Now, here finally we get to example 1, and it's one of these lousy ones that we did. Okay. I don't know why we're going back to do this, but we are. What is d by dx, I like saying that, of x cubed? 3x squared. 3x squared, perfect. Variables agree, use simple power rule. Okay? You take a derivative of something that's just a function of x. Okay? Now, d by dx of y cubed. What would that be?
3y squared.
3y squared times
dy dx.
dy dx. There it is. Okay? The variables aren't agreeing. In other words, they're having a dispute. We assume that y is a function of x. So after you take the derivative of the outer function, which is the cubing function, then, and there you took its derivative, then you take the derivative of what's inside that cubing function, which is dy dx. See, up here you sort of did the same thing, but what's inside this is x, and dx is 1. So you don't write it down, because it's 1. Like you don't write down coefficients that are 1. All right? Let's do C here. What do we do here? d by dx of 3 plus x plus 3y. Anybody? 1 plus
3 dy dx.
That's it. 1 plus 3 dy dx. Okay? Good deal. Any questions on that? Okay. So here, there is a d1. Okay? Here's the d1. What would that be then? d by dx of x y squared. What would you do here?
You have to do the product rule.
Product rule. Okay, and what would that be?
Dx
Okay.
times 2y dy dx.
Right? Yep, that's what they did. Whoa, no, not quite. Oh, they wrote some extra terms in there. Yeah, but that's what they did. Okay. What's next? Plus.
Y squared.
Y squared. Okay. Y squared times dy dx, and then the next line will then be exactly what you said. X times 2y dy dx plus y squared times 1, which then we would do 2xy dy dx plus y squared. That's about as simple as you can make it. Okay. Now, I want to ask you to do one other thing here. Since we're here, I have some space on the board. Let's do d by dx of x, y equal 1. Remember, that was the one we had originally. Will this work? We hope so. What would that be? Or differentiate that implicitly. I said it this way, but that's a little awkward. What would that be? Anybody? Help me.
Would you, before differentiating it, could you just set y?
Yeah. But I want to do it this way. Okay. We already did it the other way. I'm not going to go back in. We want to make sure it catches the same answer. Otherwise, this stuff is all wasted time, right? If you give us wrong answers. We don't want wrong answers. I don't. Because they're harder to grade. I want right answers. So how would we do this?
Product rule?
Yes. At least on the left-hand side. What would that be?
X times dy dx.
Okay. dy dx equal to, oh wait, no, I don't want to get ahead of us here. That's just the first half of the product rule. Plus y is equal to 0. No, derivative of that. We take a derivative of both sides. Oh yeah, okay. So what do we do now? Help me. Yes, move the y over, minus y. Good deal. So this will be x dy dx is equal to minus y. Okay? Divide by x. Excellent. Okay? Now that doesn't look at all like what we had last time, does it? Because we still have a y in there. But just like before and now, Dawson is sort of right, we do solve this for Diana, right? No. Taylor. Sorry. I knew better. That name popped off the page. Okay. Something's wrong here. What would we do here? Because our other thing didn't have a y in it. So what would we do here? You were saying to do it in the first place?
Make it y over 1 over x.
Y is equal to 1 over x. We know that. And you might say, if you're going to do that, why don't you do it the other way? I wanted you to do it this way. Okay. And this will be minus 1 over x, right? Which is? Anybody? Second? If you needed to, second? Huh? Not quite. Okay. It's negative 1 over x divided by x, right? How do we do a division of, huh? Negative 1 over x squared, because you invert and multiply, right? Change that to a plus, right? Minus 1 over x squared. Okay. Which is exactly what we got the other way. Okay. Just wanted to rest your mind. I knew you'd be bugged by that if you hadn't seen it. Are those the same? Yes, they are. They better be. All right. So implicit differentiation. Here's the guidelines. Differentiate both sides of the equation with respect to x. That's what we're doing anyway, right? Collect all the terms involving the dy dx. Now, I wish they'd have put in there differentiating the x terms normally and the y terms normally, but then using the chain rule and having dy dx in there. And collect all the terms involving dy dx on one side. It doesn't have to be the left-hand side. And move all the other terms to the other side of the equation. Okay, then factor out the dy dx out of whichever side it is, and solve for that by usually dividing most of the time. Any questions? It's exactly what we just did, but now they've written it out for us, but told us which side to put it on. Okay. Ready for example 2? All right, let's do this one. Find dy dx given that y cubed plus y squared minus 5y minus x squared is equal to negative 4. Yay. You think you can solve for y? Not with an awful lot of work, okay? I don't like to work hard, so let's not, okay? So what would we do then? Do it implicitly. And what would that be? 3y squared. Y prime, he likes to use the easy one, right? Plus 2y, y prime, minus 5y prime, minus 2x is equal to 0. Differentiate both sides. Now what?
Add 2x to both sides.
Yes, add 2x to both sides. The issue here is to isolate the y prime. Get it by itself, a naked y prime. Nothing else to do with it. First thing, get the terms that don't have y primes out, so add 2x to both sides. Okay, and then what would we do? Factor out the y prime. I'm going to be really lazy and do it in next step. So I'm going to pull out the y prime. What do I have left here?
3y squared.
3y squared.
Minus 3y. No. Plus 2y.
Plus 2y minus 5. And we move this over, so that's equal to 2x. All right? And now our last little step.
Divide both sides
by that parenthetical expression there. 3y squared plus 2y minus 5 divided by 3y squared plus 2y minus 5. And there's your y prime. dy dx is equal to 2x over 3y squared plus 2y minus 5. And I couldn't solve for y originally very easily, and I'm not about to try to go back and do that to get it. It's in terms of x's and y's. Okay. And that got right here. So it was worth doing. Okay. So we're still missing Fred, Josh, Elise, Ayana. Okay. Bottom part of the alphabet hanging tight there. Okay. All right. Any questions on this before I erase it? Do an implicit differentiation. We're going to see how they did it, so you'll see it in not quite as pretty a form, but you'll see it. Okay, so let's go. So what do we do first? Differentiate both sides of the equation with respect to x. That's what we're looking for. Find dy dx, differentiate with respect to x. Okay, they put this in there, which is perfectly good, illegitimate, fine. They like to write extra steps. Okay. Now, to take the derivative of this, and here's another one, we're going to do d by dx of y cubed plus d by dx of y squared minus d by dx of 5y minus d by dx of, I love saying that, x squared, and is equal to d by dx of -4. Okay. I think they've done it in gory detail here. Okay? What's that?
I'm gonna take a picture of it.
Oh, okay, yeah. Can I put the next line too? So, yeah. So you get the whole picture. Nothing but the picture. All right, good deal. So, taking the derivative of this, 3y squared times chain rule dy dx. This one, 2y times the chain rule dy dx. Minus 5 times chain rule dy dx, and minus 2x. You could write dx if you're just really anxious to write something else down, but that's 1, okay? Over here, derivative of the constant is 0, no matter what that constant is, Okay? Now what? What's next? Okay, add 2x to both sides, because it's such an exciting thing to do, but also you're trying to isolate the dy dx. So get them by themselves, anything without them on the other side. So there we did it. Okay? Next. Anybody? Help me? Factor out the dy dx. That's what we're looking for. So factor it out, isolate it. You still got to mess with it, but you got it separated from the rest of it. That would be a 3y squared plus 2y minus 5 equal 2x. Leave that alone. It's not over there. And now what? Divide by that thing that's multiplied by it, right? And when you do that, you wind up with the right-hand side 2x. They put it on the right-hand side divided by this factor here. And that isolated left by itself dy dx. Okay. Don't try to do anything else with it unless you can factor something out, simplify it. I don't think we can, okay? Even if the denominator was factorable, there's nothing you can divide out in the numerator because 2 would be the only thing and it's not divisible by 2. So that's as simple a form as we can leave it, right? I'll leave it up here a little bit longer. Any questions so far? Only new thing here is when you can't separate the y's from the x's, you're going to take a derivative. Remember that with y, you have to use the chain rule and have a dy dx. And the good news is they're always at the first power, okay? Derivative of y is always dy dx. No squares, no cubes, or anything else with them. The rest of it have that. Factor those things out and isolate just that dy dx. It almost seems like you're cheating, isn't it? It's so simple. Sort of. Any questions so far? Got it? Okay. Any others? Okay. To see how you can use an implicit derivative, consider this graph here. That's the graph of. What we just did. And what do you notice about that right off the top? What is it not? A function. Why? Fails the vertical line test miserably, okay? But you can still differentiate it. You can still deal with it. From that graph, you can get the derivative at any point. You need to know the point. You need to know that the point's on there. And sometimes that's the hard part, okay, is knowing that's on there. For instance, when x is equal to 1, your y could either be a plus 1 or a negative 3. Not a function, so it could have more than one value. So, have to deal with it. Now this one, they don't even list here. The x value is 0, the y value they don't even calculate, but it's something a little bit greater or less than negative 3. Okay? And this point here has another value here and another value there, but certainly when y is 0, x is equal to 2. Or minus 2, okay? Because you see that would work here too. When y is 0, minus x squared is minus 4, so x squared is equal to 4. Well, that could be plus or minus 2. So, what a mess. Okay? Now, this is just a little bit of a hint here. This is an even function in x, meaning that it reflects across the y-axis, and it's a neither function in y, okay, because this doesn't reflect across anything. But in x, it is an even function. Not very much helpful in getting derivatives. But you have to know the points on the curve, and if you can verify that, which is easy to do, plug in the values, but someone had to give them to you, okay? And when x equals 0 here, we don't know what the y value is, but the slope is definitely 0. Because you plug in that x equals 0 here, the slope is 0. Okay. If you plug in this value, 1, negative 3, you get a slope here very gently positive, 1/8. Plug it in and you'll see that. But you plug in this other value at x equals 1, 1, 1, and you get undefined because that's a vertical slope right there. As you would have one over here. Okay? So negative 1, 1 would also be a point on the graph. You would plug those in and see that that works, but then this derivative would also be undefined. All right. Any questions? So I said you could see if that factors. Now would be a good place to do the factoring of this, and I think it will factor, because that way it's easier to see those vertical asymptotes, perhaps. Okay. But anyway, hopefully we won't have to do many of these, right? Taking implicit derivatives, yeah, lots of those, but graphing them, rather not. Okay. It's meaningless to solve dy dx in an equation that has no solution points. For instance, x squared plus y squared is equal to negative 4. Why don't we just implicitly differentiate? Yes. X squared, the least it can be is 0. Okay, it can't be negative, but otherwise it's going to be positive. Y squared, the least it can be is 0. Anything else is going to be positive. You can't add two positive numbers or even 0 plus 0 and get a negative 4. Just isn't going to happen in the real number system. And we're not getting into complex numbers at this point. Okay, that has no solution, so don't waste your time trying to find an implicit derivative. You'll come up with something, but it'll be meaningless because that's not that function is definitely not defined. It's what is it called? Not a well-posed problem. Okay. If, however, a segment of a graph can be represented by a differentiable function, then dy dx will have meaning as the slope of each point on the segment. So let's go back here. If you had just from here on, yeah, that would be reasonable. Or from here to there, that would be reasonable. From here, you could go all the way to here. That would be reasonable. Or here to there, that would be reasonable. If you could just do a segment of it, and that segment would be represented by that differential equation, that equation, then it's how you break those up when you can't do it by domain, okay, because you can't go from negative 1 to negative infinity to negative 1 because that other stuff down at the bottom is messing with you. Okay, so anyway, but you can do pieces at a time, if that makes sense. Okay? Recall that a function is not differentiable at points with vertical tangents. Yes, we just saw that. Or points at which the function is not continuous. Yeah, discontinuous points. Okay? So, why not? Let's just skip 3 and 4 and go to 5. Well, let's not. Let's do, I don't know, this is probably not a bad place to, that'll be the best place probably to do example 3. If possible, represent y as a differentiable function of x. X squared plus y squared is equal to 0. What you think? Any thoughts on that? That's just the point. That's all. And I'm not sure that, let's see what they're asking for. Represent y as a differentiable function of x? No, I don't believe you can. Because differentiability means you have to have something there to differentiate. And this is only the point 0, 0. That's all she wrote, folks. That's the only possible value that you can put in there. And you can't differentiate a point. Which way is that going? You know, it's not going anywhere. It's just a single point. Okay? So no, can't do that. If you tried, you could say y squared is equal to minus x squared, right? And that runs into a lot of issues, right? How can a positive number be a negative number? Okay? It can't. Okay? How about this one? X squared plus y squared is equal to 1. Okay, now what they said, if possible, represent y as a differentiable function of x. Can you think of anything?
It have to be a 0 and 1.
What about a 0 to 1? That's certainly a point on there. Is that what you're saying? Yeah, x equals 0, y is equal 1. Or x equal 1, y is equal 0. Yeah, both of those will work. And how about negative 1, 1? Or negative 1, negative 1? Or 1, negative 1? All those will work too. Are they the only ones? No, I hope not. Okay? Okay, you could differentiate, but what they're asking, I think, here is write it as a differentiable function. That is not a function. If you were to graph that, that's not. What is that? Anyone recognize it? A circle of radius 1. Okay? In fact, this one up here was a circle of radius 0, which isn't much of a circle, is it? Okay? Y'all want to try hitting a baseball with 0 radius? Good luck. Okay? All right. Can't do it. Okay? You can do one of radius 1. Okay? This is a circle, not a sphere, but yeah, you got the point, I hope. Okay? So you could write this as a differentiable function of y. How? Isolate the y. How? Feel like an Indian chief. How? Okay? Yeah, subtract x squared from both sides. Okay? And you have y squared is equal to 1 minus x squared. Well, that's still not a differentiable function of y. It's not a function. But how can we make it a couple of functions? Like we said before, the end of the last thing, it said, recall the function, okay, blah, 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 blah. However, a segment of a graph can be a differentiable function. So how can we do this? Let's continue our process here. What are we trying to do? Yes. Isolate the y. How do you undo a square? Oh, okay, let's take a square root of both sides. Y is equal to? Help me? The square root of 1 minus x squared. But what do we need to do if you're doing a square root of both sides? Plus or minus. You got it. Now we've got it. Either y is equal to square root of 1 minus x squared, or y is equal to minus the square root of 1 minus x squared. So picture our circle of radius 1, okay? I don't draw circles well. I should have shown, okay, yeah. Let's call this 1, 1, and minus, all this like stuff. So here's the first one of those. That's a function. And here's the second one. It's a function. I probably should have done a different color, right? Let me do a different color. What color you want the bottom one to be? Or the top, I don't care. Second?
Red.
Red. Okay, you pick the one that's hard to pick out. There it is. Okay, we'll make the bottom red. So the blue is the positive square root, and the red is the negative square root. Okay? There, you have two differentiable functions of that which describes the same shape when you put them together. Okay? But only one of them, together that's not a differentiable function, but take either one of them and that it is. Okay. Good deal. Any questions on that? All right. That's what they're looking for. I thought their instructions were a little vague. Okay. How about this one? X plus y squared is equal to 1. Oh, let me go back to black or dark. Okay. Now, it says, if possible, represent y as a differentiable function of x. Can you? And here's the list. There you are. All right. We're doing, well, supposedly doing implicit differentiation. This is example 3, which we really aren't doing implicit differentiation for. We're just writing functions as differentiable functions of expressions or equations as differentiable functions of x. And can you do that? What was our procedure before? Isolate the y. Goodness, I can't hold on. Okay, and what would that be? How would you do that? Subtract x from both sides. Okay, and that gives you y squared is equal to 1 minus x. And now what? Square root is equal to square root of 1 minus x, missing a little something, plus or minus. So yeah, here, just like the last one, okay? But what's this going to be? It's not going to be semicircle. What's this going to be? Let's go back and look at this one. If you had solved that for x, which is not what they were asking us to do, x is equal to 1 minus y squared. What does that sort of seem like that would be? If that had been, second? Yes, a sleeping parabola, okay? It's really tired, okay? It's like this. It's opening across the y-axis, okay? And then this down here shows the top half or the bottom half. Except for, I did it wrong, because the y is minus there, it's a sleeping parabola like this, right? Because it's a minus y. So one's the top half and one's the bottom half. Because what's our domain here? That's important in most functions, right?
All except for 1.
All except for 1, okay? You only have 1 point on it, is that what you're saying?
So it can't equal.
Oh, it's not equal to what? Okay, I see. Except for what? And what does that be? Okay.
Pointing not 1, but 2.
Okay, certainly 2 is out of the picture. 1 would be okay. 2 wouldn't be. Neither would 3 or 1.1 or 1.000000001, because that would give you a negative inside the parameter, the square root. So what do we have?
X is less than or equal to 1.
X is less than or equal to 1. Everything, that's why I had to turn my parabola around this way. Anything out here is going to work. 1 will work, anything to the right will not work. Okay? Now, I do that this way. Whatever's inside the parabola, inside the radical, 1 minus x, has to be greater than or equal to 0, right? You can't take the square root of a negative number, right? So that has to be greater than or equal to 0. And then what you can do is add x to both sides. And that gives you 1 is greater than or equal to x. Or, flip it around, x is less than or equal to 1. Either way you want to do it. Or you could subtract 1 from both sides, you know, and do that way. This, to me, is a little easier. Does that make sense? So, the plus is the top half of that sleeping parabola, the minus is the bottom half. Okay? Make sense? Good deal. And they showed that to you in the book. Does anyone need me to write it, draw a drawing here on the board to see it? I'll be glad to. I'll arm wave if people at home can't see the arm wave though. Okay. There's 1/2 of that sleeping parabola. You want red again? Okay. Okay. And there's the bottom half. The bottom half is the minus. Make sense? That's a pretty ugly parabola, by the way, too. Okay. All right. Want to do example 4? Of course you do. Okay. So let me get my pen back. Example 4. I will do it. Okay. And by the way, example 4 is also found at larsoncalculus.com, and that's an interactive version of this type of an example. Determine the slope of a tangent line to the graph of x squared. All right, these are some of our favorites, aren't they? Plus 4y squared is equal to 4. Okay. At the point root 2, comma, minus 1 over root 2. Okay. This is obviously done by somebody who grew up in the computer and calculator generation. If there had been from my generation, I'd never write a radical in the denominator. Yeah, those are terrible. Okay. Nowadays it doesn't matter. Okay. I don't guess it ever really matter. Okay. Now, cynic that I am, I don't want to take your word for it. I don't want to do all this work and find out that point's not even on the graph, right? So how can you verify if it's on the graph? Plug it in, plug it in. So the x is root 2, so this will be root 2 squared plus 4 times a minus 1 over root 2 squared. The question is that equal to 4? Well, what is root 2 squared? 2 plus 4 times, and what is minus 1 over root 2 squared? 1/2. And is 4 times 1/2 is? 2. And 2 plus 2? Hey, didn't know you did such high-level math today, did you? 2 plus 2 is 4. Y'all got it? Okay, good. All right. Yes, that point is on the curve. So we can proceed. Okay. Whoa, it didn't take my eraser. There we go. All right. So the point is on the graph, so it makes sense to proceed. All right. So the question was, determine the slope of the tangent line to the graph at the point. They don't say what the equation of the tangent line, they're being really nice to you and just saying determine the slope of the tangent line. So what will the slope of a tangent line be? That'll be the derivative. Good answer, okay. So what do we do? Yes, differentiate. And what does that give us? 2x, 8, y prime equals 0. Okay, proceed. Subtract 2x from both sides. And that gives you second 8y prime is equal to minus 2x. Now what? And solve for y prime. How do you do that? Okay, done. Okay. Divide by 8y. All right, good deal. Okay, this goes out here. What goes out on the other side? That's where you step in. Okay. Anybody? Yeah, divide out of 2. Minus x over 4y. Okay, simple answer, right? As far as we can. Okay, so there's your y prime. dy dx, your derivative is minus x over, that's supposed to be an x. It's an ugly, ugly, ugly x. Okay. X over 4y. Okay. What they asked for was the slope of the tangent line at that point. Well, there's the slope of the tangent line at any point. So what do we do? Plug it in. And you have y prime, which will be the slope of the tangent line. And that will be help me, somebody. Minus the square root of 2 over 4 times the minus 1 over root 2. Boy, the calculus is so easy. It's the math that gets hard, isn't it? Okay? What do we do to deal with that? Okay, good. Were you a Marine? Never mind. That was simplify. Okay, never mind. What you got?
Well, 4 times negative 1 over square root of 2. Then divide.
Okay. Now, first thing I want to do, get rid of those minus signs. Got a minus sign, you could put that in the numerator, put that in the denominator. They go. So they're out of there. So this gives you a root 2 times reciprocal of this would be root 2 over 4, right? Is that what you were saying? All right. Now what? 2 over 4, which is 1/2. All right. That should be the slope of the tangent line, and that's just what they got to. Good for them. A little remark they have at the bottom of the page. To see the benefit of implicit differentiation, try doing this example using the explicit function, which is the one you would use, of y is equal to minus 1/2 the square root of x, 4 minus x squared, and taking its derivative. I think you'll see, give me the implicit differentiation just about any day, okay? Even though this one is, you could write it explicitly, who wants to? This is a lot easier to deal with, okay? But go home and convince yourself, okay? Sock it to it. Any questions on that before we move on to another slide? Okay. Now, example 5. Determine the slope of the graph of this one at the point 3, 1. I think you probably already guessed what I'm going to do first. Maybe not. I want to make sure 3, 1 is on that graph. Okay? Good. Okay. Let's see if it is. What's 3 squared? Plus. It is. It's what? 10 squared is? Times 3 is? 300. And what's 100 times 3? Times 1? 300. Okay. I did that last part. Okay. So yes, that point is on the graph. Okay? Thank you very much. Okay, determine the slope of the graph at that point. How would we do this? Find the derivative. Sounds like a good answer to me. So what would that be? Left-hand side. 6 times to the first power times, I wish I'd have moved over some, 2x plus 2y, y prime. All right. I'm loving this problem, aren't you? Okay. Equal okay. Yeah. If possible, always combine product rule into a single thing. It just makes it a lot easier. It makes it wrong too, but that's okay. I mean, we won't have time to figure that out, will we? Is it 100y prime? That's the product. Second, let me just do the xy separately. Take its derivative. The 100 is just a constant. I got it out front. What's the derivative of xy? Y but xy prime. And did you say something? Oh, plus y. Okay, yeah. I did it the other way, so yeah. We got it. Awfully crowded, but we got it. Okay. Oh, what a pain. Okay. Anyone have any suggestions what to do first? Okay. Before I do that, I want to get those numbers as small as possible. And how could we do that? I'm going to rewrite it over here. Fortunately, the 6 was already separated. X squared plus y squared. And in that next part, I also see that I can factor out a 2 times x plus y prime is equal to 100 times y plus xy prime. Have I done that correctly? Okay. Now, let's eliminate as much as we can. See, right now I can divide a 2 into this and make it 50. Is that okay? And I can divide a 2 into this, leave that a 3, and make this a 25. I've got the numbers as small as I can easily. So let's redo this as, okay, 3. Let's go on and do what we got to do here. You got to FOIL this thing, don't you? Multiplying 2 binomials, I don't see any way around it. Do you? Well, let's see. Now, I was thinking there might be an easy step, but I don't think there is. So let's go on and FOIL it, and we'll see what we get. Help me. x cubed got it xy squared, right? And then finally, the last is y cubed y prime, okay, is equal to, I don't see any way around our numbers either, so 25y plus 25y, no, x, y prime x. I'll do it that way since I was writing it wrong anyway. Okay, and let's go on and carry the 3 on the inside here, inside here, inside here, and inside here. Okay. Sorry about the mess, but it's easy for me to erase. It's not you. Okay, so knock yourself out. Okay, now what? Anybody? What were you saying before, Dawson? Okay, let's get all the y prime. You want on the left or right? I don't care really too much. A little bit. Yeah, let's move them to the left. Which means we'll be taking the non-y prime terms and move them to the right. So let's subtract off a 3x squared and subtract off a 3xy squared, and at the same time subtract off a 25y prime x. Okay, so we'll do a minus 25y prime x here and a minus 3x squared minus 3xy squared here. All right, so these go, those go, and that goes. So now we have a 3x squared y prime plus 3y cubed y prime minus 25xy prime is equal to 25y minus 3x squared minus 3xy squared, I think. I'm sorry? Right here. Right here. When you multiply, oh, it's a cube. Where did that come from, huh? Why did you write down a square? Tell me, okay? It's a cube. Sorry. Wait, I did the wrong one. That was a square. This is the cube. Sorry about that. Reading my writing. See, that there is where I blew it. Okay. 3x cubed. Sorry about that. Okay, I thought they should have the same power, but okay. Good deal. Now what? Factor out the y prime. And what are you left with? 3x squared y plus 3y cubed minus 25x. And what we're going to do with that is divide it over here. 3x squared y minus 3y cubed minus 25x. All right, there's my y prime. Kind of an ugly form, but there it is. Okay, and frankly, I don't think there's anything we can factor out. Anyone got any ideas? I'm afraid not. Okay, but what we're asking us to do is determine the slope of the tangent line at the point. Where is mine? Oh, I'm sorry. There it is at the point 3,1. It's this one here. I was used to it being the other. So basically, all we do is plug it in. Plug in 3 for x and 1 for y. So what will that give us? This will be a 1. Okay, let's take our time with it. That'll be a 25, first term, minus 3 is x, so that will be anybody? More like 81, isn't it? 3 cubed is 27 times 3 is 81, right? Okay. Minus 81. Okay. I'm supposed to be the one making the dumb mistakes, not you. Okay, never mind. Okay, 3 times 3 is 9 times 1 squared. I can do that. So that's just minus 9. Over, your denominator is 3 times 3 squared, which would be 27 times 1 would be 27. Minus 3 times 1 is 3 minus 75, right? Everybody got it? Or not? Okay. So let's see what that numerator is. The numerator is a minus 90 with a positive 25. Pretty sure that's a 65, negative 65. And the denominator is a minus 78 with a positive 27. That would be a minus 51. All right, well, I'm going to make that a 65 over 51. And I think I'm going to give up trying to... Did it come way off? Oh, it did, didn't it? Oh, it's supposed to be 45 down there, isn't it?
I think what happened is your y cubed is supposed to be a positive.
A positive.
Instead of a negative.
And
the denominator,
yeah, I can see that's where it needs to be, but where did, see there it was a positive here, and it swapped and became negative there. Shame on it for doing that. That would make that a plus, and now we would have a 75 minus 40. And that would be 35? 30. Be a 45, right. I was subtracting already. 75 minus 30, that would be a 45. And then reduce that. And both of them are negative, by the way. So that would be... I know that 5 will go into both of those. That would be, or minus 5, and that would be 1/13 over 9, right? 13 ninths. Yes, that's what they got. I love these nice even numbers. Okay, they're so much fun. All right. Sorry about that. That plus sign became a minus sign there for no good reason whatsoever. All right, good deal. Take your time and do it right. That's the point there. You know, don't get to rushing. Any question? Well, let's see how they do it.
I lost the minus sign, got minus 13 over 9.
You got what?
Minus 13 over 9.
Oh, minus. Okay. Yeah. Both of these, this one turns out to be an enormously negative number, and that one turns out to be a large negative number. So I think the minus is the numerator and the number. It overwhelms the positives. Okay. Well, I wouldn't accept this the same thing the book got, so I guess I will. Okay. All right, let's see how they did it, and maybe we'll find those places because they're going to do the same thing. The solution is to take a derivative of both sides, okay? Well, let's see how they do it. They do 3 times 2 is 6. They do 3, right, 6. Times this to the first power, times the derivative of the interior, chain rule, 2x plus 2y dy dx. Got that one. Equal to, pull out the 100 and then do the product rule here, and that'd be x dy dx plus y times 1. I really don't like doing y time, that makes me think it's y evaluated at 1. Okay, I know that's not what they intended, but that's the first thing I think of. Y at 1? Why are we doing y at 1? No, we're not. Okay, y is a function of x, so that's just y times 1. Okay, never mind. Now, they pulled out the 2 to go with the 6 here, and that gave us a 12. Why? Now, they did something a lot shorter than I'm. Okay, what have they done here? It is a lot easier, I think, but I've got to see where it is. Okay, they're subtracting that on that side, I think. So they're not doing this part here, they're doing this part over there. So talk about skipping steps. I thought I was, okay. This is a 6 times 2 is 12. X on the outside times x squared plus y squared on the inside. So they subtracted this part over there, and on here we have the 12. 6 times 2 is 12y times this part here, x squared plus y squared times dy dx. Minus the 100x dy dx from this side, and plus the 100y from that side. Okay. So this does look a little simpler, except they have big numbers in it. Okay, and they still haven't clarified things yet, but I guess they will. Okay, so they're going to factor out the dy dx. So I did do a little extra math there that we could have gotten away without, because I went on and multiplied. And that would be all that times dy dx. Now that's, I hate to go into another screen. This thing minus this thing times dy dx, and that's what they have at the top here, okay, is equal to 100y, same thing they got there, okay. Right-hand side stayed the same. Now let's divide both sides by this thing over here, and that will give us that. Okay. So now we plug in our 3, 1. And they like to keep those big coefficients in there. I would have gotten rid of them, or at least reduced them. And that would have been, oh, they did reduce them. Thank you very much. They divide everything by 4. Numerator and denominator. Okay? So this gives you 25y minus 3x times that. Divide this by 4 minus 25x plus 3y times that. That's the simpler form. Okay? And then we plug in the 3, 1. And after a bit of work, they tell us this graph is a lemniscate. Yay! I'm so glad that it is. Okay? Certainly not a function, is it? Okay? But pieces of it could be a function. Okay? So that would be minus 25, or 25 minus 90 over minus 75 plus 30, exactly what we got, minus 65 over negative 45, and that reduces to 13/9. That would be the slope of this tangent line at that point. 13/9, a little bit greater than 1, but less than 2. So that looks about right. I was going to graph it for you, but they did it for you. Okay, so I'm not at all appreciative. All right, any questions on that? Okay. Whoa! They must be skipping example 6 as well. How are we doing? I don't think I can. Oops. All right, we'll do example 6 here. How do we do it on time? Yeah, we got time. So let's do example 6. seems like we just did this. Determining a differentiable function. Find dy dx implicitly for the equation sine y is equal to x. Then find the largest interval of the form minus a less than y less than positive a on which y is a differentiable function of x. Okay. First they say find it implicitly. So what would we do? Take a derivative. Good answer. What would that give us? Cosine y times y prime, okay, is equal to 1. Perfect. Okay. Find that implicitly. I think the next step is pretty easy. Y prime is equal to 1 over cosine y. Now, then find the largest interval of the form minus a is less than y is less than positive a, on which the differentiable function of x, on which y is a differentiable function of x. All right, now, what they did here oh, I see, okay. And I don't see that they and this whole thing about saying of the form minus a is less than y is less than a, this says stay close to the origin. That's all they're saying there. That was just something sort of thrown in on us here. So okay. Find the largest interval of form this on which y is a differentiable function of x. Seems like the simplest thing is graph that, you know, and that would leave it done. What they're doing here is using a trig identity to rewrite this, I think it's that, yeah, as a, yeah, using a trig identity to rewrite this as a function of x, okay? And that's a perfectly fine thing to do, but if you just picture that, I mean, all you have to do is say, what does this look like, okay? Well, if this was x is a function, I mean, y is a function of x, you know how to do the sine function. Well, doing the cosine, I mean, doing x is a function of y, that is going to be positive in the first quadrant, right? Goes to, yeah, it does this kind of motion and this kind of motion here, so it's basically from here to here. And that to me is finding the function, that's what they're asking for, finding the largest interval of the form minus a is less than y is less than a on which y is a differentiable function of x. So this is the only place where it's differentiable near the origin. And where is y going from here? Well, when y is pi halves, x is 1. And y is minus pi halves, x is negative 1. So those are the 2 points. Now, what they are saying, and it's a perfectly fine thing to do, but you just have to figure out, I mean, it's sort of like they pull it out of the air, which is, maybe they pulled it out of some unknown body part. But anyway, just say this, sine, let me erase this. Okay. I can't tell you what insight they use to do this. Sine squared y plus cosine squared y is equal to 1. We know that. No matter what the x, y, or anything else is, that's always true. Solve this for cosine, and you get, subtract sine squared y from both sides. Okay? You get cosine squared y is equal to 1 minus sine squared y. And then take a square root. Ooh, the 1's supposed to be in there. And you get cosine y is equal to plus or minus the square root of 1 minus sine squared y. Okay. And then they do a little trick and say, but sine is x. Sine of y is x. So they say this is equal to plus or minus the square root of 1 minus x squared. Okay? Now, and so your derivative here would then be y prime is equal to 1 over plus or minus 1 over the square root of 1 minus x squared. So there you've turned around and gotten it as an explicit derivative, and you got it in terms of x and y, and you can see this is your derivative, and just take it from and looking at it this way, I say, why in the world did they do this anyway? So, I don't know. It seems like that's an awful lot of work to do something. If you just graphed it, you could see what the answer was. But they didn't say it. Oh, yeah. On which y is a differentiable function of x. I'm sorry. I guess I didn't read the problem. So that's what they did. No wonder they didn't show that on the slide. Okay? It's sort of like a who cares. Oh, and not only that, they don't show example 7 or 8. I think we've got time to do those too. So that one's rather bizarre thing. It seems like to me you would just say, well, here's the graph of it, there's the thing. But then the second part, on which y is a differential function of x, they didn't say find what it is, they just said on which it is. Well, there's, and by the way, you do not include these 2 points. Why not? Why don't you include these 2 endpoints? Huh? Yeah, the derivative is undefined. The function values are defined, derivative is undefined. Okay, so it has to be, and their example, they put minus a is less than y is less than a, good for them, because you can't define it at that point anyway. Okay. So, I'm sorry. Okay. We'll leave that. Unless y'all have some real gnawing problems with why pursue that any longer, I'm perfectly happy to leave that one alone. All right. Let's do example 7. Finding a second derivative implicitly. Okay, I'm trying to think. Did we have that earlier? No, we did second derivative back here, but I don't think we did it implicitly. Okay. So this is sort of something new here. With implicit differentiation, the form of the derivative can also be simplified, blah, 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 by an appropriate use of the original equation. That's what we kind of did there. A simple technique can be used to find and simplify higher order derivatives obtained implicitly. So let's try it and see what they say. Given x squared plus y squared is equal to 25. Do y'all have any vision that comes to you right then? A circle of radius 5. Okay, good. You're having the right visions. Okay. Now it says find d2y dx squared. Okay. And certainly I don't want to do this explicitly. I think we saw that was going to be pretty ugly. So let's try doing it implicitly. So what would we do first? Take a derivative. Excellent. What would that be? 2x plus 2y, y prime, equals 0. Excellent. Okay. Now what? Okay, let's first deal with this one. Okay. Next thing you would do, in some order. Second? Yes, subtract 2x. I'm sorry, my hearing's so bad. Subtract 2x from both sides. Okay, that gives us 2y, y prime is equal to minus 2x. Now what? Second? Divide by 2y. And that gives us y prime is equal to minus x over y. All right. There's your first derivative. Okay? Now, taking a second derivative is not too bad here, as far as I can see, so there's nothing real special here, except how you do it. How do you want to do it? Second? Quotient rule certainly looks like the straightforward way. You could also do a minor adjustment and do a product rule, but whichever way you prefer. So let's do the quotient rule since that's what you said. So y double prime would then be simply what? I'm going to put the minus out front. How does it go? Second? Y. Why not? Okay. Y times 1, is that what you're saying? Yeah, okay, I got it. Y. Minus. X. Y prime over y squared. Okay? All right. So I'm real tempted to flip that minus sign around. Well, wait. Yeah, still think maybe not yet. Okay? Not yet. This will be a minus. Okay. Find d2y dx squared. Okay. Now let's leave the y in there. That will be minus y minus x, but we know what y prime is. So let's put that in there. And that would be another minus x over y. Right? Yay or nay? Okay. Okay. Times y squared. Over y squared. Now, I'm real tempted to do this. From my original problem, I know that y squared is equal to 25 minus x squared. Are you okay with putting that into the denominator? No reason not to, is there? So let's do it. 25 minus x squared. I don't know that's any better, but it's there. And I think we're just about there. So that would be a minus y plus x squared over y over 25 minus x squared. Now, they may not have done that, and there may not be any reason to do that, but I just thought it looked like a simple thing to do. And to get that numerator in terms of, here's something I want to do. I want to get rid of those minus signs. So let's make this, let me do two things at once. Let's put least common denominators together. Won't that be a y squared plus x squared over y for that numerator? Everybody with me there? Over, and I'm going to take that minus sign and reverse the denominator, make it x squared minus 25. Is that all right? Okay. Okay. I think I'm going to go backward on something here. This will be, let's go back and call that y squared. Okay, why not? This will be y squared plus x squared over y cubed. That'll be easier, won't it? Is that what they get? Okay. But what is y squared plus x squared? 25. Oh, that was a minus y squared. Sorry about that. Those minus signs, they'll sneak in there and bite you where you don't want to be bitten. Okay. Minus, because remember, I had flipped it around. This was my y squared, not that. Okay, so this is the minus y squared. So the minus sign still shows up. So minus 25 over y cubed. That looks way too simple, doesn't it? But sure enough, that's what it turns out to be. Does everybody see that? All right. Now, I don't know why. Oh, it's time, isn't it? The graph in figure 232, which is at the bottom of the page, we haven't gotten there yet. It's called the kappa curve because it resembles the Greek letter kappa, they say. Okay, fine with me. General solution for that tangent line was discovered by English mathematician Isaac Barrow. The only reason I know Isaac Barrow was he was the Lucasian chair of mathematics at Oxford University when he had this young whippersnapper student come in named Isaac Newton, and after a few years he said, look, that guy ought to be the chair, and he turned the chair over to him. Yes?
Are we still getting the test today?
What's that?
Are we still getting the test today?
Yes, we are. Okay. I'm glad you want it so badly. Okay. So we'll begin next time with example 8. Homework exercises, any of the odds 5 through 19. They're all at Calc Chat. 5's at Calc View. 21 or 23, they're all at Calc, both at Calc Chat. 23's at Calc View. 25 through 31, all at Calc Chat. 25's at Calc View. 33 or 35, both at Calc Chat. 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat. 39's at Calc View. And you can stop somewhere there and we'll pick up the rest of them later. I don't know. Let me get you your test before you leave. And I apologize. It's probably just about as easy as the first one. You probably feel like you're not getting your money's worth. Oops, we'll stop there. Okay. Oh, man. Terribly old and stiff in the joints. Okay. Pass one back. Pass one back. Pass one back. Just pass two back. Right. Yes, as soon as I get all the first test in, that's exactly what I was going to harp on next. I want to get the first test back to you, but I don't have them all in yet. So I'm still missing 1, 2, 3. Okay, thank you. All right. All right, good deal, thanks. I have a feeling some people not here haven't turned in the first test yet. Yes. 1. Wait, I'm in the wrong class here. Okay. I just got Dawson's in. Yeah, Josh isn't here. I don't have his. Lace, I don't have hers. And I just got Anna. So as soon as I get 2 more in, I'll be able to give you those back. All right, good deal. Thank you much.